Gnanam paramam dheyam. Knowledge is supreme.
Okay. Yes, sir. Wait. All right. So far we have arrived at the transformation matrices for two operations. One is identity, one is reflection. Next we are going to discuss the matrix for rotation, and from there we will go and talk about something called your reducible and irreducible representations. We will see what that means. So the question is, can we not have an operation in some other plane, if I have translated it right? So yes, you can. So what you could do is, you have used these three planes, one is this, and one is this. You could think of operation reflection for any other plane, okay. But the question is, does the plane have to go through origin? Yes, it does. Otherwise, it will not be a symmetry operation, because origin is the center of the molecule, right. So if you put it anywhere else, then that can never be a symmetry operation. We are talking about symmetry operations here, okay. But what you could do as an exercise is that, think of a different plane. Say this is x axis, this is x axis, this is y axis. Think of this plane and see how they will change, and then you will reach some interesting. Why don't we do it? I was not planning to do it, but let us do it now. Okay, now I will draw it in this way. This is x, this is y. Okay, let us talk about this plane. Say at 45 degrees. If you perform a reflection with respect to this plane, then what happens? X, y, z. First of all, it goes to z, the way I have drawn it, right. So z does not change, z remains z. What about x, what about y? X becomes y and y becomes x, right. What is the matrix now? 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay. Now, I hope the difference between the matrices we got earlier and the one that we have drawn now are obvious to you. What is a major difference between this and this? The first one is a diagonal matrix, this is not a diagonal matrix, right. So here you have non-zero off diagonal elements as well, okay. I was planning to discuss this a little later, but since we have reached here, let us discuss it right now. What is the meaning of a diagonal matrix? What is the meaning of a non-diagonal matrix in this case? So a diagonal matrix means x remains x, it can change sign or it can remain itself, okay. So very simple symmetric antisymmetric relationship holds. Y remains y or becomes minus y, nothing else is possible. Z remains z or becomes minus z, nothing else is possible. The moment you have this, what is the meaning of this term? X has become y, y has become z, right. Now you have interchange of coordinates, that is what it means. If you have non-zero off diagonal elements, that means that you have contribution from a different coordinate in the transform coordinate of the particular one, okay. That is the meaning of non-zero off diagonal elements, and that is what we see in a little more detail when we discuss rotation, okay. Let us talk about rotation. Just for the sake of convenience, see, I do it in some coordinate system, you should be able to transform from any coordinate system to any other one, okay. That is just a matter of mathematical exercise. So what we will do is, we will try and find the coordinate system that is easiest, more convenient for us, that is all, okay. Now let us say that we are talking about rotation Cn and just as a matter of convenience, let us say that this Cn is along z direction. Okay. Now, what will happen? For a matter of convenience, again I will write x1 y1 z1 and x2 y2 z2, where x1 y1 z1 are coordinates of the point that we start with. We are working with the position vector, and let us say I have rotated by an angle theta, any angle theta. It is not necessary that rotation of theta will take me from first coordinate to fourth coordinate. I could have gone here, I could have gone here. All I am doing is a clockwise rotation, and we will just keep this as an acute angle, but exactly similar discussion will follow if the angle is not acute. Okay, you can work it out yourself if you want. Okay, let us say we are rotating by an angle theta. What is theta then? This is Cn axis and rotation is theta. So, theta is 360 degrees by n. Okay. So, theta is not just any angle. Now, also let us say that this angle is alpha. In that case, what is x1? x1 is the x coordinate of the point in its initial position, initial point. What is x1? Angle between the position vector and x axis is theta, sorry, alpha. What is x1? Okay, r cos alpha. R cos alpha. I will just not write that arrow, it's okay. What is y1? What is y1? See, you have to give me the answer, otherwise I will write whatever comes to my mind. R sin alpha. Okay. What is x1, x2? If this angle is theta, this angle is alpha, this of course is theta minus alpha, isn't it? What is x2? First of all, the way I have drawn it is x2 positive or negative? Positive, right? Is y2 positive or negative? Negative. Let us remember that. What is x2? Length does not change, just because I have rotated, length cannot change. Length is r, this angle is theta minus alpha. So, what is x2? Yes, Divya? Oh, okay. x2 is the x coordinate of the transform point. x1, y1 denote the initial coordinates. The question was, what is x2? x2, y2 denote the coordinates of the transform point or transform coordinates. Okay. So, I have started with this, I have done a rotation by an angle theta, I have come here. Okay. Tip of my finger is the point. So, coordinates of the tip of my finger here are x1, y1, x2, y2. Okay. But maybe we can get z out of the way before that. What is z2? z2 is equal to z1. I might as well write that. So, this one will be definitely 0, 0, 1, right. When I do a rotation with respect to z, what I get is z coordinate remains unchanged. So, this last row is going to be 0, 0, 1. What about x2? If this angle is theta minus alpha, help me. I will write the thing I know, r. Length does not change, r. Then what do I write? Cos theta minus alpha, and y2 is r sin theta minus alpha. What I will do is I just put a minus sign here. Okay. Now, not very difficult to expand this. What is cos theta minus alpha? Tell me. Cos theta, cos alpha minus plus, very good, sin theta, sin alpha. Okay. Now, see, what is r cos alpha? x1. So, x1 cos theta what is, who is going to write R here? What is R sin alpha? Yeah, y1 sin theta. So, I have my first equation, x2 is equal to x1 cos theta plus y1 sin theta. Second equation actually, because we have already written z2 equal to z1. Is this clear? Now, can I write the first line here? First row, can I fill that in? So, what is x1? Sorry, what is x2? x1 cos theta plus y1 sin theta plus 0 into z1, right. So, I have got 2 rows already, I will now fill in the second. Same way, y2 equal to minus r sin theta minus alpha. So, minus r, what is sin theta minus alpha? Help me. Sin theta cos alpha minus, but there is already a minus here, plus r. So, yeah, sin alpha cos theta is okay. Again, r cos alpha is x1 and r sin alpha is y1, right. So, I got minus x1 sin theta plus y1 cos theta. What will the second line be then? Minus sin theta cos theta 0. Okay. So, this here is your transformation matrix for rotation by angle theta. Point to note, z here is the unsocial coordinate, it does not mix with x or y, z remains itself. However, the action of Cn is to mix x and y. This is something that we need to understand very clearly. Do we understand this? See, what was the action of this reflection? Identity anyway leaves everything the same. When we did the reflection here, there was no mixing of coordinates, right? X either remained x or became minus x, same with y, same with z. Here, however, when you rotate, it is not very difficult to see that mixing of coordinates take place, right? The transformed x coordinate cannot be represented just as something multiplied by x, right? There is a contribution of the original y coordinate also. Same is true for the transformed y coordinates. So, what Cn does is it differentiates, it kind of classifies your 3 coordinates into two classes, one xy, other z. Okay? Z remains by itself, does not mix with anything, x and y mix with each other. Of course, if your axis of rotation was x instead of z, then x would have remained the unique coordinate, y and z would have mixed. This is the first thing that we need to understand. So, when we talk about an axis of rotation, we denote them as Cn, right. So, suppose the axis of symmetry is such that you have to rotate by 180 degrees, we call it C2 axis. Where do I get this number 2? It is 360 by 2, 180 is 360 by 2. If I rotate by 120, we call it C3 axis. Where do I get the number 3? 360 divided by 3, alright, understood? Okay. Any other question at this point? No? Then let us do something, let us recall what we had said about the planes of symmetry of C2V and C3V. Do you remember C2V and C3V? In case of water, it is a C2V molecule, the planes are like this, one plane is sigma V, one plane is sigma V dashed. What had we said? They are non-equivalent planes, their actions are different. Okay? They belong, another way of putting it is they belong to 2 different classes. The word class has its origin from the formal group theoretical treatment, we do not have to go there. For us, it is enough if you understand that equivalent symmetry operations belong to the same class. Okay? What about ammonia, C3V? The 3 planes are equivalent, right? 1, 2, more flexibility is required, 3, right? 1, 2, 3. What is the axis? Do you see what is this axis? That is at the juncture of the 3 planes, C3 axis, right? What does the C3 axis do to the planes? It can interchange the planes, right? You can just imagine the third plane. Okay. So, that is another way in which you can define equivalent symmetry operations. Symmetry operations that can be converted from one to the other are equivalent. Okay. Now, I want to make one more point that you know already, the C3 axis. Okay. Better draw on the board, because otherwise again I will need a 360-degree rotating shoulder. So, see what I am trying to say is this. I am talking about the C3 axis. Where is the C3 axis? Here. Hey, look here, forget the time. This is the C3 axis, right? Let us say I have 3 atoms A, B, C. These are the 3 hydrogen atoms of ammonia. Okay. I can do a C3 operation like this. C3 axis, A, B, C, 3 hydrogen atoms. C3 takes it, A goes to B, B goes to C, C goes to A. A, B, C. Okay. I can do it again. I can do another C3. Then what will happen? C comes here, A comes here, B comes there. Okay. So, this first operation is called C3. Second operation, you can think you have gone from here to here directly. This is called C3 square. This rotation by 120 degrees, rotation by your 240 degrees. There is another way of thinking of it. This is clockwise rotation, and if I do an anti-clockwise rotation, C3 minus, then also you get there. Okay. So, crux of the matter is, associated with the C3 axis, you have 2 operations, C3 plus, C3 minus, or C3 and C3 square, in whichever way you want to put it. And these operations actually belong to the same class. Do you agree that C3 and C3 square belong to the same class? Same kind of operation, right? They belong to the same class. What I would like you to do is, I will give you the answer, but you work it out yourself. This here is the transformation matrix for Cn plus, right? We have taken a clockwise rotation. I ask you to work out the transformation matrix for an anti-clockwise rotation. Okay? You will get something like this. For Cn minus, the matrix will be cos theta minus sin theta 0 plus sin theta cos theta 0 0 0 1. Okay, just you do not have to believe me on this, work it out yourself, you will get this. And while you do it, I encourage you to work out different kinds of angles. Do not stop in making this an acute angle, make it an obtuse angle. Okay, you will get the same answer. All right. And this leads us to an important conclusion. Do you know what is the character of a matrix? Trace. It is something like this, sum over AII, right? You add the diagonal elements. What is the sum here? 2 cos theta plus 1. What is the diagonal here? Again 2 cos theta plus 1. This is a manifestation, not proof. This is a manifestation of a very important principle, that for symmetry operations of the same class, values of character are the same. Chi is the notation that we are going to use for character or diagonal. So, why do we call this character of all things? We could have just called it a trace or a sum of diagonal elements or something like that. Why character? Let us wait. We will see that these are actually unique properties that are going to allow us to perform a systematic treatment of symmetry in molecules and in spectroscopy. So, the name character is actually justified. They are unique properties of these operations. Okay. We will elaborate upon that a little later. For now, it is enough if you know that the sum is called a character, and as long as you have understood that we have demonstrated, not proved, that for symmetry operations of same class, characters are the same. Now, so what we have arrived at is transformation matrices for identity, reflection and rotation. Now, what we want to do is this. So, what is this? We are giving numbers, right? So, and we said that these are characters, these are markers of symmetry operations. Now, I have a basis and I have several symmetry operations in a point group. These are sort of like, we can say, the grades you score. Okay. Even though I do not believe in it, but generally you use grades to decide whether a student is good or not. So, when you do that, is it enough to take up any random course and look at the grade of the student? No, right? Because I can get A in one and FR in everything else, or the other way around. So, that is why we have this concept of SPI and CPI, isn't it? What we do there is, of course, they are necessary evils. Don't get personal about SPI and CPI, but we are just demonstrating. We are doing a philosophical discussion here. No personal business. So, when you want to assess some student quantitatively, then it is not enough to look at the performance in one course or one semester. That is why you do this CPI business. Same is true for the symmetry operations. You want to know how a basis transforms. It is not enough if you look at only reflection, only rotation or something else, only inversion. What you want to do is, you want to get a holistic picture and you want to develop an idea of how the function behaves as a result of each and every symmetry operation. And the collective information that we get from all these matrices is called a representation. So, a representation is somewhat analogous to your SPI or CPI. Okay. We will do it very quickly with one example, and then we will come back next day and we will elaborate upon it. Water, C2V molecule, right? I will just draw it once. This is what we are talking about, a C2V molecule. This is your C2 axis. Let us define this as Z. Okay. This here is X, this is Y, this is Z. Okay. What we will do is, we will use the basis X, Y, Z for this system, and we will see what kind of transformation matrices we get. Alright, so far so good. What are the operations that are there? E, C2, which is Z, sigma V. The way I have drawn it, which one is sigma V? The way I have drawn it, the molecular plane is ZX plane, right? So, sigma V is ZX. X axis is on the board, Y axis is perpendicular to the board. Sigma V, ZX, and sigma V dash then will be YZ. Okay. What we want to do is, we want to work out the transformation matrices for each of these symmetry operations using X, Y, Z as basis. So far so good. Can I start? First one we will write without even discussing. E is done. When we apply C2, what happens? Usually you would expect a mixture of X and Y, but this is a special case because your axis is C2 axis, 180-degree rotation. So, what happens is, each axis becomes negative of itself as long as you are talking about X and Y. and z remains the same. Agreed? So, minus 1 0 0 0 minus 1 0 0 0 1. Are we comfortable with C2? What happens when I apply Zx? We have discussed already, the axes that are on the plane will not change sign and the axis that is perpendicular to the plane will change sign. So, y will change sign, others remain the same and there is no mixing. So, 1 0 0 0 minus 1 0 0 0 1. Okay, and I might as well write that one, that is yz. So, x will change sign, y and z will remain the same. Minus 1 0 0 0 1 0 0 0 1. What we do is, generally we call the molecular plane sigma v and we call the perpendicular plane sigma v dashed. It is just a convention, nothing else. As long as you understand zx and yz, you are good. The reason why we put that dashed is that they are not equivalent planes. So, if I write both as sigma v, we might make the mistake of thinking they are equivalent, they are not. That is why we put a dash on that sigma v. So, what do they have to do? Yes, yes, they do. Okay. So, what is asking is these two matrices have the same trace. So, how is it that they are not equivalent? That reminds me of this cliched story that everybody has heard. Somebody went as a witness in a case where a hen was stolen and the judge asked how big was the hen, the guy said this big and the judge of course blew up. And then when the judge got really angry and all, the other guy said, wait for my second hen. So, now the second hand, remember what I said? I said that symmetry operations belonging to the same class have the same trace, same character. I did not say the converse is true, right. So, that is my second hand in this hen stealing case. Are we comfortable with the matrices? Now, we'll arrive at representations. So, first of all, see what has happened. In the basis that we chose, x, y and z, the basis is such that no symmetry operation causes a mixing of the basis element. See, the matrices are such that the basis elements do not mix with each other and they either remain the same or change sign. So, they are either symmetric or antisymmetric. Okay. So, what I can do is now I will erase all the zeros. This is called the method of block factorization of matrices. What I can do in these matrices is that I can draw these lines, okay, same kind of pattern that you used to draw in tic-tac-toe. And what I find is that I have been able to block factorize. If I take all the 1 1 elements, right, they are non-zero, right, 1 minus 1, 1 minus 1. I take the 2 2 elements, 1 minus 1 minus 1 1. I take the 3 3 elements, 1 1 1 1. All other elements are 0. Okay. This method is called block factorization. You divide all the transformation matrices in the same way so as to leave out these 0 elements to the maximum extent possible. Okay. Very qualitatively, this is block factorization. Alright. So, what I will do is I will even erase these. Okay. Now, see, think about x. How does x transform with each symmetry operation? It is symmetric with respect to E, antisymmetric with respect to C2, symmetric with respect to sigma v zx, antisymmetric with respect to sigma v dash yz. Okay. Instead of saying it in English, what I can say is that for x, I have the combination 1 minus 1, 1 minus 1. For y, it is 1 minus 1 minus 1, 1. Symmetric, antisymmetric, antisymmetric, symmetric. For z, it is 1, 1, 1, 1. Symmetric all the way. Okay. So, now this is a representation. In fact, if I look at the matrices, the entire matrices, that was also a representation. Okay. You look at all the matrices that are there, transformation matrices, collectively they form a matrix representation. What we have learnt is how we can reduce a representation to smaller dimensionalities. Okay. So, what I am now saying is that for x, it is 1, what was it here? Minus 1, 1, minus 1, do not need this anymore. For y, it is for z, I remember it is 1, 1, 1, 1. For x, it is 1 minus what? Oh, 1 minus 1? Oh, I did not realize you are trying to help me. Sorry. Thanks. 1 minus 1 minus 1, 1. Excellent. So, now see. This 1 minus 1, 1 minus 1 is the representation for x, 1 minus 1 minus 1, 1 is the representation for y, 1, 1, 1, 1 is the representation for z. Those of you who have worked with character tables would perhaps recognize that this looks exactly like those rows that are there in character table. Actually, we have arrived there. So, there is one out of these representations which is special, and that is the one with z. All characters are 1. Okay. What is the meaning of all characters being 1? It is totally symmetric. So, this representation is called the totally symmetric representation. No matter what you do, the function does not change, it remains symmetric. These are not totally symmetric representations. What we learn next week is how to give what are called Mulliken nomenclatures to these things. Alright. So, here what we have been able to see is if you use x, y, z as basis, then you end up with 3 one-dimensional representations. What is the meaning of dimensionality? How many basis elements are there for that particular representation? You end up with 3 one-dimensional representations. X, y and z are completely separable in this point group at least. Next day, what we will do is we will use the atoms as basis and we will see what kind of representations we get. Alright. Until then.